for the delay. We are struggling with these computers again. But I want to first ask for questions about anything. Thank you for coming. I know you're worried about the exam on Wednesday. Don't worry too much. Learn stuff and you'll be fine. And enjoy it and have some good fun. I wanted to make first a couple of comments on material that's gone by already, and then move on to new things on quantum mechanics, mostly the wave nature of matter, which is the key new idea, a fantastic idea, and remarkably fruitful. But the first thing I wanted to say was just a few words about why quantum effects were not observed earlier. Why did it take till 1900 for somebody to notice this? The fact that particles had wave nature, or that waves had particle nature. Well, first of all, it's as we've been saying, it's pretty hard to imagine things having both of these qualities at the same time. But the other thing that I think you should appreciate is, first of all, is the quantum large or is it small? And it's both. Again, it's one of those strange things where if you look at it two different ways, you get slightly different answers. Namely, what Planck, well, of course, his first idea was that if you have a black body and you look at the oscillators in the black body, or the shaking of the black body as a whole, think of waves in the black body, and they are radiating, well, all over the place. The ones that radiate inside have time to rattle around and come to thermal equilibrium, which is why we deal with the black body, is because we want something simple. If a thing is not in equilibrium, it's changing in time, and it's much more difficult to understand. So he started out with the simplest case that he could imagine, namely just waves rattling around, and they've come to a temperature, things have steadied out, and you then just measure the radiation that's somehow coming out of these oscillators. So that's what Planck's idea was. He was worried about the oscillators here. And he said that with all these different kind of oscillators in the body, that they couldn't have a continuous energy, which is, again, a surprising idea, because if I have a spring and I'm pulling it, it's an oscillator, and I could think I could make it a little bit more oscillating or a little bit more continuously changing its energy. Why not? But he says that apparently that's not so, and that an oscillator of a given frequency can only have energy levels which are 1 HF above it, 2 HFs, 3 HFs. That's what he said. And if you do that, also you could have, of course, many oscillators in the walls, some of which have big energies. So they have a very high energy. And again, he says, no, well, the energy between levels of this guy, too, are also separated by a finite amount, a quantum of energy. And on this model, he could explain the radiation coming out of the box. As I've explained to you, you put in a certain amount of thermal energy, somewhere in here, say. This is heat, supposedly, these oscillators would get going. The thermal energy, kT, kB, the Boltzmann effect, thermal energy per particle is too low to start these oscillators going. Therefore, coming out of this body, you will have these frequencies, yes, but these frequencies, no. So if you look at as a function of frequency, the emission, it looks like this. These oscillators are working, the low ones, because they have enough energy from the heat, and these ones here don't. And that's how he explained this turning down of the emission with frequency, which is inexplicable by classical ideas. Then Einstein took the thing one step further and said, well, if these things are emitting energies in proportion to HF. Maybe the light itself has an energy given by HF, H times the frequency, and Einstein actually says it very well. I actually read his paper the other weekend, and he says it very well, that in the creation and the absorption of the light, it acts like a particle. He doesn't, because he knew that light is a wave in other aspects, namely diffraction and interference. So he didn't put it as graphically as Muhammad Ali, that you float like a butterfly in between and sting like a bee at the beginning and the end. He didn't know about Muhammad Ali, and he wasn't a boxer, by the way. He was a sailor, so he knew about blowing with the wind. But anyhow, but Einstein actually says it very well. He paraphrases, float like a butterfly, sting like a bee. He says when the particle starts out and when it ends, it acts like a particle. But in between, it acts like a wave. He actually says it right in his first paper. And that's the picture I have derived. Yes, sir?
Why does emission decrease as frequency?
Oh, because you see, in order for this frequency to be emitted, this oscillator has to oscillate. You have to have a high-frequency oscillator oscillating. A high-frequency oscillator in the box, of the box. In other words, the material of the box has to oscillate at that frequency, and then it'll raise like an antenna. So you have all these little antennas in here, and some of them are high-frequency antennas, and some of them are low-frequency antennas. And when those antennas vibrate, they radiate at their own frequency. That's the model. Very simple model. Not at all exactly like the way real materials are, but it should give something like the right answer. And this was how he got it. Yes, go ahead.
So I understand why the gaps get higher, so we get lower frequency, like not as much of a higher frequency.
Yes.
But how come we have less on the other side, even though the gaps?
Oh, that's a very good question. The question is, why does it go down on the low frequency side? Well, the reason is that it has to do with the number of possible oscillators at low frequencies. The number of possible oscillators, if you have a box like this, actually it's in my PowerPoints, if I can dare use this thing again. It goes back to the idea of no, it's not that far back. Here it is. See, if you have a long wavelength vibration, it turns out that there are very few long wavelength oscillations within a shape. But you can get a lot more high frequency oscillations. It's sort of, you remember the Chladni mode things? Some of you weren't here. We had a demo where we had a plate and you vibrate it, and the plate has modes of vibration. It was a square plate, and we just vibrated it up and down with a sort of a speaker. And the plate, on low frequencies, you can have a mode like this, for example. It'll vibrate like that. But you see, at high frequencies, you can get this mode, and you can get modes this way and this way. You get a lot more modes at higher frequencies. So this is folding together the stimulation of the mode and the number of modes. And it turns out that the number of modes goes up very steeply. And that makes this result even the weirder. And you see, that's why theorists had gotten the result that at high frequencies, you have a lot more modes, and they should be excited, and they should be radiating, and it should go to infinity, but it doesn't. But down here, it's because there are fewer modes. It's a very good question, actually. And a very brilliant scientist, Lord Rayleigh. So you're in the Lord category now. Very brilliant guy. Did this calculation, the so-called Rayleigh genes calculation, where he counted up the number of modes. he said, if I have a vibrating body, what are the number of low-frequency modes? And as they go up, how many more do I have? And all of them should get going, and it should be a catastrophe up here at high frequencies. And it wasn't so. But that's the answer to a very, very good question, actually. So this is the number of modes going up, and the excitation goes up, and then it cuts. But even with a larger number of modes, because there's no energy, their need for energy is so great, they cut off too. So that's very good. Okay, so we come down to Einstein's idea, and so Einstein says this relation was able to explain, for example, the photoelectric effect. So on the one hand, we think the quantum is small because it's never been noticed, and yet it's large enough to do something. So let's just do a quick estimate. So suppose we had the frequency of light, say visible light, which is roughly in the range of 500 nanometers or so. What number do I use? Okay, let me use 550. It's a very common nanometer. Is sort of the center of the visible range. A nanometer is 10 to the minus 9th meter. Okay, so let's get the energy of such a wave of this thing. So it's multiplied, it's h times f. Now h, Planck came up with roughly 6.6 times 10 to the minus 34 joules seconds. He got that number by just working out the shape of this curve, and he just fit the curve, and he needed a value of h, this hf. He needed a value of h, and he just fitted the curve, and he came up with a number very close to this 6.6 times 10 to the minus 34, and that fit the curve very well. So he said, well, that's what we'll use. So let's us do it. And so the actual energy then, now the frequency is c over lambda. The usual velocity is equal to frequency times lambda, wavelength times frequency. So let's just put the numbers in here, and you get 6.6 times 10 to the minus 34 joule seconds. And the speed of light is 3 times 10 to the 8th meters per second. And the wavelength we pick in the visible, as an example, 550 times 10 to the minus 9th meters. So the meters cancel. Per second cancels second. Very nicely, we come up with an energy in joules. Let's see. So 3 times 6.6 is roughly 20, 21 maybe, over roughly 5. Let's just do it roughly. And the numbers up here, 10 to the minus 34 and 10 to the 8th is 10 to the minus 26. And divide that by, we call this one 5, so I've moved it over, so it's 10 to the minus 7. So when you work it all out, it comes out something like 4 times 10 to the minus 19 joules. Well, we don't have a very good feeling, perhaps, of how much energy a joule is, but anything times 10 to the minus 19th is going to be pretty small. So that's a pretty small amount. In fact, let's see just how small it is. Let's consider, suppose you're out in the sunshine and on the middle of the day, and the sunlight were coming in on you. A certain amount of energy is being delivered to you. It turns out that in the middle of the day, the flow of energy is about 1,000 watts per square meter. That's the intensity of light. That's actually quite a lot. That's why maybe solar energy might be useful, is because the sun is actually pouring in 1,000 watts per square meter, roughly, on a clear day at noon. So how much, let's ask, how much energy arrives in 1 second? So the energy is equal to this, the power, this is a power actually, per square meter, power, watts. So that's 1,000. A watt is a joule per second per square meter. Let's say the energy times 1 second. The power times 1 second. So let's ask how much energy arrives in 1 second. So let's multiply by 1 second just because it's easy. So we get 1,000 joules per square meter in 1 second. But and let's say the average, let's say it's visible light, so the average energy might be for each photon. Now each photon, on the average, each average photon, we said, is going to be the order of 4 times 10 to the minus 19th joules. So if we divide, this is the number of joules per photon in a way, right? So if I divide this energy in a photon into the total energy, I should get the total number, the number of photons is, say, 1,000 joules divided by, say, 4 times 10 to the minus 19 joules per photon. So I'm getting sort of the order of 2 times, let's call that 10 to the 2, and 10 to the minus 19 is 10 to the 21. I'm getting sort of, or 2 times 10 to the 21 photons. So, standing in the sunshine, you would be struck per second by 10 to the 21 photons. And, it doesn't feel like much. You just get nice and warm, but that's a lot of photons. Which says the photon must be really rather small, right? If 10 to the 21, that's a lot. I mean, a billion is 10 to the 9th, so it's it's 1,000 billion photons in a second would strike you in the sunshine. So it sounds like it's small. On the other hand, think of it this way. This number here, if you were an electron with a charge of if you're an electron with a charge of Q, it's 1.6 times 10 to the minus 19th Coulomb. We remember that one. You see, if you put that electron through the energy, potential energy of such a thing is equal to E times V. So if I put let's see, to get a photon's worth of energy, let's say to get a photon worth of energy, 4 times 10 to the minus 19 joules. To get that energy, I have to multiply 1.6 times 10 to the minus 19 coulombs times a voltage, which is roughly this is about 2, so it's approximately 2 volts. A volt being a joule per coulomb. Right? So now a photon looks rather bigger. A visible photon delivers as much energy to an electron as giving it 2 volts of energy. 2 volts. So that's considerable. And in atoms, the energy differences are of the order of volts. So this photon energy, though it's small on some scales, on the scale of electrons and atoms, it's considerable. And that's why delivering a photon of this energy, this is the energy per photon, to an electron can give it 2 volts of energy. And so if an electron were being held in a material with 2 volts down in the well, that photon comes in, delivers 2 volts. It can lift the electron out of the well. You sort of see that? Think about it a little bit, but you see that it's sort of understandable why, on some scales, the energy looks small, but on the other hand, on the scale of atoms and electrons, it's quite a considerable energy. And you can imagine if I don't use 500 nanometer light, red light, let me use ultraviolet light, which is maybe 10 times more. Now the photon is coming in with effectively 10 volts or 20 volts of a thing. You put in an X-ray, it's coming in with hundreds of volts, and it can really do things. It can, for example, if the bond in a molecule is sort of on the range of energies of volts, which it is, it could break bonds. Single photon delivering that much energy, as they say, as a unit. So it's a very, it's good to realize it's doing things both ways nicely. Now, I wanted to do a couple of things here back to our general introduction to particles and waves. So here we have all of Planck's stuff, explanation of black body, and the importance of the black body radiation. Again, the sun's radiation is at one very high temperature, and it comes in the visible. We, at 300 Kelvin roughly, we radiate here, and then we have all these atmospheric absorptions, which limit the outflow of energy, which is a good thing and a bad thing for us. It's a good thing. It keeps us sort of warm at night and keeps the temperature from getting too high, actually, during the day, too. So that's a very important application of the black body radiation. Each of us is emitting in this range around 10 microns of radiation. So it's very nice to know that because there's so much talk about it these days. Okay. Then we have the idea that Einstein came up with, that the light could come in as a whole, and when it interacts with an electron, all at once it gives all its HF of energy to the electron and can knock it out of materials. And different materials have different depths. They hold the electron to different depths. Cesium, I think, maybe is about the order of a volt, and tungsten might be very much deeper, and so you would need maybe a higher frequency to knock an electron out of tungsten. That is represented by the material's work function, or it's usually symbolized by phi. So different materials have different abilities to hold the electrons, and we get this result. And Einstein explained that very well. Here is another effect. This was actually in the 1920s. It wasn't really believed that this was true. The experiment came along, and this was verified actually by an American, Millikan, at Caltech, that the Einstein equation worked. But there were still doubts. In fact, Millikan himself had his serious doubts what he was doing, what his result proved. Well, when they gave him the Nobel Prize, maybe it made him feel better. But everybody had their doubts. And then along came another American, Compton, who showed a very peculiar thing, which also was controversial, and that is he shined in X-rays into materials, and he measured the wavelength of the X-ray that came out. Now, what he found was that the X-ray that came out had a longer wavelength than the X-ray that he's shown in. Now, that was very surprising because classically, if the X-ray is a wave and it comes in and it shakes the material should shake and send out the same wave. Scatter what you shake me this way, I'll release that. But his didn't. And the way he explained it, he said that what's happening is that the wave is coming in with a certain frequency and wavelength. It's an X-ray, actually. It hits an electron, and it knocks the electron in some direction. It scatters off in another direction, but it gave some energy to the electron. So that if the energy is related to the frequency, the wave should have lost some energy by conservation of energy. If this electron was sitting there and all of a sudden it's coming out with some speed, a half mv squared, it's got some energy, so the wave must have lost energy, meaning its frequency would go down if the energy of the wave was related to its frequency, which was, of course, the argument at the time. But the fact that the wave frequency went down, namely the wavelength went up of the scattered wave, was a very direct proof that the energy of this wave is related to its frequency, because this is a lower frequency. This went down, so it lost some energy. And that Compton effect won him a Nobel Prize as well, and he became a very prominent American scientist. He was involved in the committees to build the atom bomb and all this kind of. He's a very good man, and he was very gutsy to come up with this effect and confirm the idea that the photon energy was proportional to its frequency. And here's another idea that I've mentioned before, and that is that Einstein also showed that if you have a frequency, it doesn't matter that it be light. It could be other things. It could be a solid vibrating. And if, for example, you lower the temperature on a solid and you don't give it enough energy to excite its frequency, it does not absorb energy anymore, because then you're down below. In other words, if you need this much energy in a solid, h of the frequency of the solid, this would be the actual sort of lattice vibrations of the atoms against each other. And if you need that much energy, but at low temperatures here, you don't provide that at kT, well, you don't excite the oscillator. Again, if you just put in this much, it's not enough. And the oscillator does not absorb energy. And so the amount of heat that flows into the material drops down. And I showed you also this picture of hydrogen gas, where, again, there are a couple of frequencies involved here. And if you don't put enough energy in, the oscillators don't absorb, and the so-called specific heat drops down. So these ideas were confirmed, and they were argued about, and this and that. But finally, everybody now seems to believe it. And then the crucial thing in explaining the matter waves, the idea came along in 1924 by the famous de Broglie, which I demonstrated with an oscilloscope, and we sent an electron beam through a material and scattered it, diffracted into rings. And there were bright rings and dark rings and bright rings, which could only be explained as an interference effect. So again, the matter, electrons, were being, they were floating like a butterfly. They were waves in travel. But when you finally record them, they come in as spots. I'll show that a little bit later, too. So we'd had that demo. And the point is that it turns out that all massive particles have some wavelength with them, because the formula says that the wavelength is related to the speed of the particle, but also its mass. So if you have a light particle, it turns out the wavelength is simply longer. It may be easier to see. But we've used particles up to buckyballs even, which is 60 carbon atoms. And I have to maybe brag a little bit here, but this may be interesting for you too. As biologists, I was once involved with a thing called Langmuir-Blodgett films. Has anybody heard of Langmuir-Blodgett films yet? You should know about these. It's a very, very nice thing. It's kind of a simple biological membrane. What it is a hydrocarbon. There's a long chain. It's just simple carbons, 18, for example, 18 carbons, and hydrogen sticking out. So it's a totally saturated hydrocarbon, at the end of which is a carboxylic acid group, COOH. And the H is acidic, so if you put it in water, the hydrogen can go off, leaving behind a negative group at the bottom. So because it's ionic at the bottom, it's kind of hydrophilic, it's ionic, and the long chain is hydrophobic, so like it's oily. So sometimes these are called surfactants because they stay at the surface. The head is ionic, sort of goes into the water. It's hydrophilic because acids like to go into water. Ionic things like to go into water. It's a very simple idea. And then you have so it's sort of like a life jacket on a thing. And they tend to float with the head in the water. And if you put enough of them on the water and you squeeze them together, you can get them to kind of line up like this. So you can make a packed layer, which is like a biological membrane in a way, which is ionic at one end and hydrophobic at the other, as I understand. And the cute thing is what Ms. Blodgett did. She was one of the first to get a PhD, first woman to get a PhD in England. Well, she was an American, but she went to England at the urging of Irving Langmuir, who was a great chemist at General Electric, but he saw her talent, and she got it. But she got the idea, well, maybe I can get that film off the water. So you just put in a plate, which is itself hydrophilic, like quartz or glass, and it attracts the ionic end. So you put that in, and you push on the film, and the ionic end sticks to the plate, and you can pull the film off, so you can deliver a biological membrane, one membrane at a time, with your own hands. It's really nice. I've done it. I was doing these experiments, and my own game was to attach a magnetic ion to where that minus end here. If I could attach a magnetic ion here, I could lift the ion out with the molecule and deposit one atomic layer of magnetic ions at a time. And so I would have what I called a two-dimensional magnet, which had never been done before. Of course, there's just one atom layer, and you do it with your own hands in front of your eyes. You got to do it gently, but it's not, you don't need a gigantic vacuum system and all that stuff. So I was making these two-dimensional magnets for reasons of physics reasons. People were theorizing about what happens if you go in low dimensions. Well, let's do it. So we made two-dimensional things and studied their properties. But I happened to give a talk at Oak Ridge National Lab where they have an atomic pile, and in the atomic pile they make a lot of neutrons. So there was one fellow who was using beams of neutrons to study materials. So he said, well, neutrons, I should step ahead one thing. We had done at my lab, which was at IBM at the time, we had an X-ray, a very good X-ray specialist at low-angle X-ray diffraction. And it turns out that this molecule is 50 angstroms tall, the long chain, or actually, no, it's 25, but you get a double layer, so it's sort of like the unit cell is 50. But in any case, so if you do the formula, n lambda is 2d sine theta, the Bragg formula. So you have layers, but the layer spacing is sort of like 50 angstroms between, say, heads, tails, head. That's sort of a unit cell. So you see that's sort of the repeat distance. Well, if you put in a big D like that and you have an X-ray wavelength, you get actually a very small sine theta. So namely, the and sine theta is this thing here. So you have to come in at a very low angle, and you need a very special X-ray machine for that. And my friend at IBM had such a machine, and we studied the X-ray diffraction of these things, which we did to down to one monolayer. You could actually see one monolayer with X-rays, which was a shock to the community at the time. But when I went to Oak Ridge, the fellow there says, well, I have neutrons. I said, well, neutrons, they have a wavelength too, right? Why don't we try neutron diffraction off these things? Just using the analogy that if it's matter and it's moving, it has a wavelength. And it turns out that the wavelengths are similar to the X-ray wavelengths we were using. So I made some samples and sent it to him. See, the wavelength for the neutrons, what they do with the neutrons is they let them strike the reactor as they're going out. So again, they have a chance to come to thermal equilibrium. They may be starting out fast, but when they bump into the into the reactor, they take the temperature of the reactor, which is room temperature roughly, and the wavelength gets quite short. See, my X-rays, my friend's X-rays were at 0.1 nanometer. The neutrons that this other fellow had were at 0.4. Well, that's not too bad. It's about a factor of 2. So you just put in a factor of 2 here, and you see, well, maybe it's doable. Again, low angle, but maybe doable. So we did it, and it's kind of interesting. So here's the X-ray diffraction. Now, X-rays, we have a lot of X-rays, and here I have, 42 layers, and you see these diffraction peaks. Now, there's very big orders of magnitude difference, but there's a peak, and there's a whole bunch of peaks in here. These are all those little subsidiary maximums that you saw with your optical gratings. You know, if you had 2 layers, you have one thing. If you have 3 layers, you get a little bumps in between. Well, with 42 layers, you get like 40 bumps in between. So here are the 40 bumps, this dark little spot here, 40 bumps in here, which tells you how many layers there. So you could actually count the layers. So here's 40 bumps and a big peak, and another 40 bumps predicted. Can't quite see them in this case experimentally. But so you get this nice X-ray picture, again, at low angles. See, it's 3 degrees, just skimming off the surface. And but the kicker that I wanted to show you, you can do this with X-rays and nobody's surprised, but then we did it with neutrons. And again, we just use the same calculation to see all the peaks here. Those are the subsidiaries, but you get these nice predicted, nice fat sharp peaks. Again, the wavelength of the neutrons giving you diffraction. And indeed, the dots, again, neutrons not quite so abundant as the X-rays we had, but you can see that it does reproduce reasonably well. We don't see the fine structure here. We don't have the detail. We don't have quite the fine control of the wavelength as we did with X-rays. But anyhow, I just want to show you that matter particles have wavelengths, and if you work with it, you can get it. Now, so here's some more stuff. You can read about it. Okay. Now, this is a very interesting point that I wanted to make with you that has to do actually with so-called Heisenberg uncertainty relation. Has anybody heard of that? Yeah. Some of you all have heard of it. Okay, and it's almost taken on a mystical character in the sense that some people think that what it tells you is that, well, first let me say what it is. What we think it is. Anyhow, other people have interpreted it funny. What it says is that if you try to localize an object within a certain distance, you can only know it's a momentum within a certain range simultaneously. So if a thing is localized in a certain space, then its momentum, meaning mv, well, let's call it m delta v, there's an uncertainty in its momentum. Now, the honest interpretation of this is that these are simultaneous measurements, so you can't know both simultaneously. That is, because one measurement disturbs the other. Now, this is misinterpreted to say that precise knowledge is not possible. Some people have put it that way. That's not what this says at all. It says if I have precise knowledge of this, I have no knowledge of that. That's all it says. It's not that I can't get precise knowledge. Just that if I really want absolutely perfect knowledge of this, I just have to give up knowledge of that. So, but I can know any one thing perfectly well, and that has been misinterpreted. But I wanted to tell you why this is really sort of obvious from the point of view of if matter is a wave. Because if matter is a wave, then it becomes obvious that a wave is by its nature not localized. So this law becomes really obvious. And other people have noticed this too, but Heisenberg went about proving it in a particular sophisticated way, but I think you can do it much better. In other words, if let's say I have a wave, Now, if it's a perfectly sinusoidal wave and doesn't begin and doesn't end, if I ask you where is it, it's everywhere. So, but you see, a perfectly sinusoidal wave has a particular single wavelength, and so by the momentum is given by this. If I know wavelength perfectly, I know the momentum perfectly. And so if I have one wavelength, I know the wavelength perfectly, but I don't know. But then delta x is infinite because I don't know where it is. It could be the uncertainty of where it is. In fact, it's everywhere. The range of where it is infinite. If I have single wavelength, right? Does that make sense? In other words, the wave starts at infinity, goes to infinity with a single wavelength. I've perfectly defined the wavelength, perfectly defined the momentum, but the wave is everywhere. Its range, its position is everywhere. On the other hand, if I localize the particle here, and I know it's here, how do I make that out of waves? No one wave can give me that. So I need a lot of waves to localize something. And I'll show you that. Let me see if I can come up with a very nice program here. Let me, for the moment, put this away. Let's see. Let's see where it is. Ha, ha, ha. Let's see, maybe it's over here. No. Nope, it's the wrong one. Where is it? Excuse me while I look for it. No, maybe it's in here someplace. No, here it is. Sorry, folks. Yeah. Now, let me try to make that. So here, what the game is here. This is rather cute. I'll give you the location of it. What this is, we are trying to create a localized situation, namely a square wave. The particle is like here, and here, and here. And the question is, what kind of waves do you need number of terms? Let me reduce the number. See, what I'm going to be doing is creating this shape by adding up sine waves. And the trick is that if you get enough sine waves, you can make any shape you want. So here, for example, I'm starting out with one sine wave. You see, this is sort of the spectrum of sine waves. And you see there's one sine wave. The basic sine wave gives me a peak and a valley and a peak and a valley. But that's not really a square wave yet, by no means. But suppose I add another sine wave. Well, that one doesn't give me anything. It turns out that even and odd matter here. You'll see, if I add the third and fourth, the second wave, you see that sine wave has a, I can't do both. It has two peaks within the square wave, whereas this one has one peak within the square wave. So by putting in two peaks, I sort of square it up a little bit. And you see the shape looks a little bit better. If I put in, now I have three peaks within the square wave. If I put in yet more number of terms, let me add more terms. Okay, in fact, I can do this with sound. This is very interesting. So the point is that this is the fundamental. If I add more waves, which you can now see and hear. Now I'm adding another harmonic. And I've shaped up the wave quite a bit. And if I add more and more harmonics, I can make the wave, by adding all these little waves, I can make the shape more and more precisely what I want it to be. That's kind of an annoying sound, isn't it? Sorry about that. Let's see. That's more human. Okay, but the point is that it's again this Heisenberg argument. If you try to make the shape more and more precisely localized, you're going to need more and more waves. And that's exactly what this is saying. If I want to localize this, then if I want this to be small, I have to have a large range of wavelengths. Now, this is a very important idea, not only in quantum mechanics, but also in in real life. Let me maybe turn this off entirely. I hope that idea is demonstrated pretty well. Now, the point I wanted to make is that in real life, what's going on out in the world is that in order to, I want to explain to you AM and FM radio in 1 minute. Namely, the point is that if you just send a signal like this on a radio, you just get this one tone, which doesn't have much information except that I'm here. You know, if the people who are looking for extraterrestrial life, if they heard something like this, they'd be thrilled. But there's not much information there except that there's somebody beaming a single frequency at you, which is already would be something for them. But for us, who, if you want to hear music, da-dum, da-dum, dum-dum, you can't just do this. Because this is just But if you want to have you have to modulate that signal. So you have to put something on the carrier. And when you do that, you're adding wavelengths. So in order to make that shape, just as I make this pulsing shape, you have to add wavelengths. And that is what we call bandwidth, because you need a width of frequencies around the carrier, which means that the carriers can't be right on top of each other, which means that you need space between the radio stations, which means that you use up the whole spectrum, which means that a fight starts. Like, who's going to get the space? You don't need one frequency, you need a band around that. And so you need, as much as possible, as large a band as you can get, which means that you need large frequencies. That's why we went from radio to FM to microwaves for your cell phones, to light on optical fibers, go higher and higher frequencies to give us frequencies and bands around each frequency to transmit variable information. So this is a very important idea, and it has simply to do with the superposition of waves to give you a shape. Like if you want to have a pulse, a very narrow pulse, like this delta x here in time or in space, if it's a traveling wave, it's going to need a very large delta lambda, lots of frequencies, in order to create this, because you're going to have to cancel out a lot of frequencies in order that just one of them pops up. And they all interfere, and you get a net something where you want it. And that requires all these bands, all these frequencies. And that's what we have, like the Federal Communications Commission and other people like this who argue about who's going to get the bands. Oh, by the way, there's a talk after this, which I think the first 5 or 10 minutes might be valuable to you, because it talks about the idea, if you have a wave, how does it suddenly become a particle? I mean, this collapse of the wave function, like we've been saying, it floats like a butterfly but stings like a bee. Well, how does it do that? How do you change from a butterfly to a bee? And so that's partly what the subject of the next colloquium is going to be. I think I'm going to sit at least for the 15. So I would sit in the back row. I'm going to sneak out about after 10 minutes, but because it gets unless it's very understandable, which it may not be. Okay, see you next time.